Hello and welcome. It is day 2 of the October challenge, and you're on a stack of books, kind of precariously. I'm using index cards to lift it up slightly. um, it's been a long day for me. I tried to get a certain video done, trying to customize my microphone, and that ended up taking longer than expected, but I guess that's the point of these challenges. I'm gonna pivot, do something easier. So, I hope you all get nice and restful, nice and comfortable. Take a moment to just find the right spot. I'll be telling you about how the internet works tonight, and I hope this nerdish rant is comforting. I'm gonna take a moment. I'm gonna take some nice deep breaths, just 3 of them for myself, but please feel free to continue. I don't mind at all. Let me get started. Deep breaths really do just take all the stress away from the body, you know? But let's get started with the internet. One of the first things I like to tell people about the internet when trying to explain it, see how it works, is that the internet was made on purpose. It wasn't by accident. A lot of people think that it was made much the way that old village roads were made, you know? A guy had a house here with a door here, and another guy had a house there with a door there. I walked from my house to his house, and he walked from his house to my house, and that path, the easiest, shortest path, is now the road. The grass giving way to the steps and creating a natural, compacted earth path. And some smaller networks are made that way. And probably in the early days of the internet, it was made that way as well. But the modern internet, as we know it, was made much more intentionally. It was made as a piece of infrastructure that was designed and purpose-built. It's a lot less of a town's dirt path and a lot more of the US's interstate roads, the freeway system. It's this large, incredibly fast piece of infrastructure that many years of both planning and execution to connect all the major cities and create new major cities across the US. Now, I like trains, let me specify that. But the US does have a car freeway system. And that's how the internet works in a very broad way. So, now that we know that the internet was made on purpose, that means we also know that it was made with intention, which means there were problems along the way. Some things don't make sense because it didn't make sense then, and some things make perfect sense in a weird way because they thought about it ahead of time. They designed for it, they looked ahead. And that'll help us along the way to really understand what was going through their minds as they made the internet. Because there were other ways to make the internet. I think as the internet was coming to fruition, I was not alive then, but many people could tell you that there were other internets that were competing, other large networks, infrastructures that wanted to be built and be the internet. But we have the one that we have now. And let me tell you about how it got made. If you want to connect one computer to another, because they want to communicate, it's not too hard. You just plug one into the other, right? We're ignoring the hardware and software of everything. We're just talking about concepts. But yeah, you take one computer, plug something in there, and plug into the other computer. Two computers is super easy. You don't need to know where it's going. You just need to know that it's going out of your computer, right? Your computer just needs to know that when it receives something, that it automatically knows it was from that other computer, because there's only one other computer. And same goes when it comes to sending it out. It doesn't need to know where that signal's going. It just sends it out. And that other computer will just capture it, because again, there's only one other computer. So everything's fine and dandy there. If we increase the two computers to 3, it's much the same, but we have a new issue. One thing is, you're going to need 2 wires. You're going to need, 3 wires, 2 out of each computer, which isn't too bad, you know. One, you can think of a triangle, and one computer has one going to the left and one going to the right. And each of them do that. And well, that's also not too bad. You just now need to kind of assign which computer is which. So you can say, computer to my left and computer to my right. It doesn't take too much effort to do that. You just need to know that if I'm sending out of this way, it'll go to that computer, and if I receive it that way, it came from that computer. You don't have to give it a name or anything. It's just left and right, 1 and 2, or however you want to label it, A and B. But just that way and that way. So not too bad. Increasing to 4 adds new complexity. Now you need 3 plugs for each computer, 1 to each go to each one. And that's still relatively doable. You see many computers today with that many ports, and sure, ports aren't too expensive. So we can just keep plugging them in, one to the next, to the next, to the next. But there's so many now that we might actually start receiving data at the same time between them, and it becomes a little confusing. Who's who? Where? Who? Wait, I thought I received this from that guy. I thought I received this from there. How do I deal with that, One way would be to turn everything else off. So you talk to one computer and you say, hey, that computer, I want to talk to you for a moment. And that computer says, yeah, sure, yeah. I'll talk to you too. And so you close every other port, stop talking to all the other computers, and only talk to that one. And that can work for very small things, very momentary things. But eventually, you're going to realize that that's not good enough. You want to be able to talk to multiples of them at relatively the same time. So what you do is you give them all a name, or in our case, a number. You just number them 1, 2, 3. And you tell them all, hey, whenever you send me a message, put your number ahead of it. I'm number 1 computer. Here is my message. That way, whenever you receive the message, you can say, oh, this is from number 1, this is from number 2, this is from number 3. And you get a number 2. Your computer is number 4. Lovely. So that's not too bad. You now have a mailing system, They can just send things to you and you know what's going on. If we increase it to 5, however, we start realizing that, okay, 4 ports is just way too much. Sure, you could still have it, but that's just a lot of resources being spent to just connect to every single computer. So, there's a couple ways to solve that. One way is you only connect to your left and right, as if there were only 2 computers. So, the same scenario, or as if there were only 3, I mean. So the same scenario you had with 3 computers where it's only left and right. But in this case, everyone's in a ring, right? One after the other, in a daisy chain. in a nice little ring. And what you can do is you still label everyone. You have a number, you have a number, you have a number. And as long as everyone agrees whose numbers is whose, you can just send the data along the daisy chain. You take the data, it says number 5, that's not me, I'm going to move it forward. You take the data, it says number 6, that's not me, you move it forward. Or we only have 5 right now. This is for number 1, that's not me, move it forward, but then you get one for number 4, and that is you, so you keep it. And same goes, you can have your data and say, oh, this is actually for number 2, and you hand it to whoever's to your left. And you just go in that circle. All the data keeps going in a circle, in a circle, in a circle. And that works all right for 5. But if we go up a little bit more to around 6, realistically 6, you could keep going with the chain, especially with modern technology. But if you keep increasing again and again and again, let's call it 50. If you have 50 computers, the chain becomes a lot less reasonable. Because although everyone only needs 2 ports, what can happen is if you cut the chain in one place, everything is, let's start with this. With 50 computers, the chain is so long that if you have the person to your right is the one you're trying to communicate to, and you send your data to the left, going through all 50 computers will take a long time. Maybe your computer can kind of keep a memory, take educational guesses. You know what, that one's much closer. So you can make it so that it's only ever going halfway. The ring, 25 computers. But that's still quite a lot. You're essentially hoping that every computer along the way is powerful enough to deal with everyone's data at all times. And that's just a lot, every computer having to deal with 25 computers worth of data is just a lot to deal with out of the 50 computers. And so that just stops making sense. And there's also another issue with the ring, is that if you cut it in one place, one of the connections gets severed, whether a computer goes down, gets broken, or someone physically cuts the wire, it still works, but now it doesn't matter how good your guessing is. You have to go through all 50, You can't go halfway to 25. You'd have to go either forward all the way or back all the way until you reached yours, because it's not a ring anymore. It's like a horseshoe. And then if you cut it again in another place, snip, you now are left with more like 2 half circles. And you can cut it in different places. You can end up with 1 isolated computer, 20 isolated computers. Those 20 computers can still talk to each other, but now they can't talk to the rest of the 30 computers because 2 wires were cut. And that just breaks the whole system. So the ring stops making sense pretty quickly as scale goes up. And again, we're designing the internet here. We see that networks and computers are going to be huge. Around the time they were making it, the telephone existed, and we see just how amazing the telephone is and how many people have telephones, how amazing long-distance communication is. So we're really looking ahead here. We're thinking on the scale of at least millions of computers, if not more. So if we're already starting to see issues at around 50, 100, 200 computers for the ring, we need to come up with another system. And that's where we start introducing something called a switch. Now, a switch, you can think of, actually gets its name from the telephone systems, the big switchboard. Now, if you remember, or you don't remember, you might, but if you can imagine how old phones work, you'd pick up the phone and you'd talk to a person and you'd say, hey, operator, I want to talk to the dentist down the road. Maybe you gave them their number, right? Similarly, how we're describing this, that dentist has a phone number, a network has a computer number, and you tell the operator, I'd like to go talk to the phone number 17, And they'd say, yeah, sure. And they connect your phone, number whatever you are, and connect you to 17. And literally they had a wall of just plugs, all labeled with everyone's phone numbers. And they'd plug in from one place to the next, wherever you are to where you want to go. And they'd ring the phone. And so a switch does much the same way. So if you have a bunch of computers, instead of connecting them one to the next, left and right, you have them only have one connection, going from them to the switch. And so the switch, its job is to do what the operator did back in the telephone, which is to take requests from a computer, see where it wants to go, and send it that way. And we're starting to see what a modern, home network looks like. If you look at the back of your router, there's more modern ones provided by your internet service provider. Probably has 2 ports on there, and that's a switch. There's 2 ports. You can plug in 2 computers on there, and you don't even have to be connected to the internet. They'll talk to each other just fine. But yeah, so you stop doing the ring, and now you have what's called a star pattern. So you have the center switch, and you have all these computers connected to the switch. And the computers only need one connection from them to the switch. And the switch is a specialized piece of equipment, so it's perfectly fine for it to be built with just nothing but ports. That's totally fine. Now, we do still run into an issue with scale. We solved the issue with this circle or with the ring, where if we cut certain computers off, have them turn off, that breaks the network. In a star pattern, each individual computer can turn off and break however much it wants. Everyone else isn't affected. It's fine. They're perfectly okay. They can still all communicate with each other. But we haven't solved the scale issue. See, you can have one switch with like 50, ports, but very quickly you're going to realize that you probably want to separate out computers. So maybe in one business or one building, there's about 100 computers. But then in another business, in another building, there's another 100 computers. Now, you could theoretically just plug them all into a switch. They both pay for it or something, whatever they want to do. But that's not really too realistic, You don't want to make it so that if the connection gets severed between one of the computers, they need to go to the centralized switch that's far, far away, that's difficult to deal with, right? You want to make it so that the switch, which is where your computer is directly connected to, which will be one of your more common failing points, to be really easy to maintain access and all that. So each kind of network each bundle of computers should have their own switch. So because of that, you have this star pattern with a switch and a bunch of computers connected to it. And you have this other star pattern with another switch and a bunch of computers connected to it. How do you get the switches to communicate with each other? Now, you could plug one switch into the other, and that'll solve some issues, a good amount of issues. But the problem is that if you have one computer here that's numbered 1, 2, 3, and it sends it to the switch and says, I want to talk to computer 17. The switch doesn't know if it should send it to number 17 in their network, or if they should send it to number 17 over there. And that's where we start getting into routers. So a router, their job is to kind of, route things, They help switches communicate with other switches in a basic sense. Well, actually, routers communicate to other routers. Again, another thing of because it was designed intentionally, you could put, kind of just have one switch send it to the next router if you only have 2 switches. But you want to have your own router. So you have one router in your building and one in this building, because you want to make sure that you're able to maintain it and work on it. It's a piece of your own infrastructure. And so the routers are able to communicate with each other. And the way they do that is that they assign router numbers. So the router knows that I'm number 1 and that router is number 2. And so the switch inside of your network doesn't need to know if it's going to 17 outside or if it's going to 17 inside. It just needs to know, am I going to 17 or am I going outside? And so that simplifies things, because what happens when you have 200 computers here and 200 computers here and 200 computers here and 200 computers here? That adds up quickly. Those numbers add up quickly. And can get confusing, especially when you don't agree which number is which. So this switch just needs to know, hey, am I sending it to someone inside of our network in my switch, or am I just sending it to the next, or am I sending it to the router? And the router can then say, oh, I can send it to the other router. And that router can send it to their switch, which will send it to their computers. So now you have this ring. You have a switch in the middle, all the computers connected to it, and you have that switch connected to a router. And that router is connected to the next switch, which is connected to their own, or that router is connected to the next router, and that router is connected to its own switch, which is connected to its own computers. And the router helps deal with things too. Instead of having it lets you have multiple switches in your network that can all agree and work together, but also know that, hey, we should send it to a router to go to the rest of the internet. So what happens with the rest of the internet, though, as you increase in size and size and size and increase, is that router needs to connect to not just the next router, which is where it wants to go directly. It's not just going from router 1 to router 2. It needs to go from router 1 to router 1,000. Because again, we want to design the internet to work across 1 million devices, at least. Tens of millions, hundreds of millions, billions, or trillions, actually. Which is why IP addresses exist. IP addresses, Internet Protocol address. It's like your home address. You don't get to decide what your home address is, kind of. It's based off of which house number you are, on what street you are, on what state you are, and what country you are, and so on and so forth. So an IP address works much the same way, where it allows the routers to know where it needs to go through other routers. Now, this stuff of how routers talk to other routers, I'm be real with you, kind of over my head. This is where the real internet part comes in, and there's some funky math that's involved on how to get from one router to the next, to the next, to the next, so that it gets to the router it needs to get to. But essentially, that is how it works. It figures out, hey, out of this address, I need to go this way, this way, this way, this way, this way, this way, to get to that router. And that's what it does. It just gives instructions using that address along with a few other instructions and says, hey, send me this way. And it sends it until it receives it. And that router goes, oh, I know what that's for, and sends it into its switch to be sent to its computer. And that also allows you to number things independently of where the network is, right? All you need to do is number the routers, and that's the only part that needs to agree. But once you're past your network's router, your switch can have its own number. Each of your computers can have its own number. You don't have to be computer number, 17,437,508. You can just be computer 1, computer 2, computer 3. Which is why, or that that's helpful not just with like numbering computers to know which number you are. It's also helpful when you're working on things, because I can, it's a lot easier for me as a technician to remember that, like, oh, your address isn't, however, 3, 12 numbers long. I don't need to remember your unique 12 number thing. I know that yours is probably going to be 192.168.0. Was something, and that something, that last few numbers, is what I actually need to know. Helps standardize things, it helps put that together. It also lets me know ranges. IP address ranges IP address is this, giant list of numbers, and they have certain areas of it that they cordon off. They're like this number to this number. This is used for something specific. And being able to reuse numbers in that way for each, section of a network is really, really useful for that purpose, where we can agree that, like, hey, I'm going to use this number, a 169 address, to signify that I'm not connected to the wider internet. I'm just connected to another computer. And by seeing that address, it helps me troubleshoot things. It helps with knowing what type of network the computer is seeing and is setting up, and also lets computers know that, hey, oh, that's the type of connection you're sending me. Yeah, sure, I can deal with that. So it works really well. You can see how, like, it's just a series of connections that we do to try and make sense of it, to just kind of manage all those connections. But to help us manage those connections, we also need to go through security. Let's talk about that for a moment. So when it comes to security, one of the big things we do is we encrypt things. And encryption, if you're not sure, is basically just scrambling up all of your data in such a way that only you and the people that you want to be able to unscramble it are the only ones who know how to unscramble it, right? Basically, I have the key and you have the key, and that key is just knowledge. It's not a physical key. And because it's knowledge, it can be duplicated infinitely for whoever you need it to know. And at the same time, because it's knowledge, it's a lot easier to change. If I realize that someone who I don't want to know knows it, I can just change it suddenly and not tell them the new one, and only tell the people who I want to know the new one. And now the key is changed very quickly, very immediately. And that works really well when you need to send things that you don't want other people to magically see. Because if I'm sending my stuff through my router and my switch, that's fine. If I'm communicating within my own network, it's not too bad. Sure, there's still some ways, especially if you're a larger business. Again, this is starting to seep into real world. Like, why was it designed this way? Because the real world is kind of fucky. And that is, you still encrypt things within your own network, because someone can just connect to your network without you knowing. If you're a big enough network, if you don't know what you're doing, or if you're just kind of naive, you just give people your Wi-Fi password, don't really think about it. Now they're in your network. And if your stuff wasn't encrypted in some way, then they could just look at the traffic. And similarly, because you're using other people's routers, other people's switches, that's how you have to send data. If I'm going through my router to the internet's routers, whatever it is, magically, to your router and your switch, I have no clue what you're doing with that. You could just be looking at whatever open air data there is there, if it was open air, and just see exactly what I was doing. So that's why we encrypt things. So you can, get this box of data all jumbled up, shaken up in a way that you don't know how to deal with, but you still see the address. It's perfectly readable. So you're like, oh, well, here, go to the address, right? The worst you could do is just stop it from getting to the address, which is annoying, but fine. Um, so security works in that way, which is really nice. And most protocols nowadays are encrypted without you even knowing it. The big one, of course, that was getting advertised were VPNs, virtual private networks. If you ever hear a VPN as like an advertisement, just kind of forget about whatever they're saying. They're selling a product, is what you need to know. They're telling you, they're basically saying, I'm selling you an engine, even though they're selling you a Toyota, a Camry from Toyota, right? They're selling a full blown car with all its own features, with its own design, but they're saying that they're selling you an engine, which is more of a concept, more of a general thing. So a VPN in the more general concept, wider IT world is basically just a digital cable, a virtual cable. So you have your own private network in your house, you have your Wi-Fi router with your switch and your router, and that connects to all your devices, and that's fine, that's private. But once you get out of the world, you need to be careful about your data. So a VPN encrypts your stuff and lets you send, again, that jumbled box of stuff through everyone else's routers. And once it gets to your router goes, oh, you want to connect as if you're in our home network? You're encrypting correctly? Coolio, let's do this, Instead of having to, drag a physical cable from like your home to the library, so that you could still connect to your private network without having to connect to the library's network. You can instead just use a VPN. You're using all the library's stuff, but because your stuff is encrypted, it's all good. And that's why the product isn't really too useful with how it was being advertised in the beginning. In the beginning, they were saying, oh, you're encrypting and you're keeping your stuff safe, and it's amazing. And when in reality, if most stuff that you use on a day-to-day basis on the internet is already encrypted and already kept safe, very safe. Modern VPNs as a product, the ones that you buy, you should just think of them as just a way to act as if you were in another country, which is what they do. They, instead of connecting to your private network, how a VPN works, they sell you a product to let you connect to their private network, which can be in different countries, and that lets you, do whatever you want in that country, because you're acting as if you're in that country. All your data is being sent to your router first, and then your router is being sent to the world. Rather than just going from wherever you are and straight to the world. Beyond that, there is some more stuff when it comes to like scale. We actually, or the people who designed the internet actually, I think they planned for like trillion or so, a couple trillion devices. And that's what IPv4 is. That's your 174 address, your 192.168 address. And that actually wasn't enough. They ran out of numbers on the IP address. And so they actually created IPv6, which is the new one. It's the one that kind of is just unreadable. Or like you can read it, but it's just not easily remembered and such. And that's just used for the wider internet. Because again, they ran out of numbers. So they were like, oh shit, we should really come up with a lot more numbers. But thankfully IPv4 is still used in a lot of networks that isn't the wider internet, and makes life much easier to deal with. But yeah, that's how kind of basic networks work, how the wider internet kind of works. It's just a giant web of agreeing to send stuff to where it needs to go. It's the post office, it's telephones, it's whatever piece of infrastructure you can think of that lets you go from where you want to go intentionally in a relatively efficient path. It's just with computers. But yeah, it's really interesting stuff, I think. And I hope you're asleep by now. Have a wonderful evening.